Hello, and welcome back to Math 112, Calculus 2. Our topic for today is alternating series, absolute and conditional convergence. Let's talk about alternating series and the alternating series test. The series, sum from n equal 1 to infinity, negative 1 to the n plus 1 of b sub n, equals b0 minus b1 plus b2 and so on, converges if the following is true. The b sub n's are all greater than 0. B sub n is greater than or equal to b sub n plus 1 for n greater than capital N, and the b sub n's go to 0 as n goes to infinity. Let's take a look at an example. How about the alternating harmonic series? We had seen the sum of 1 over n before. By the integral test, the harmonic series, the sum of 1 over n, all positive terms, diverges. Now, the sum from n equal 1 to infinity of negative 1 to the n plus 1 times 1 over n is an alternating series, and it satisfies all of the conditions of the alternating series theorem, which essentially says that you require that the 1 over n on their own be all positive. 1 over n has to go to 0. And the negative 1 to the n plus 1 makes it an alternating series. So by the alternating series theorem, the series with the negative 1 to the n plus 1 in it converges, even though the series sum 1 over n with all positive terms diverges by the integral test. Now let's take a look at another example. The sum from n equals 0 to infinity of negative 1 to the n over 2 to the n. We see that this is an alternating series, which satisfies all of the conditions of the alternating series theorem. So it is going to converge. But we can even say more. This is also a geometric series, the sum from 0 to infinity of negative a half to the nth. And if I apply the geometric series theorem, I get that this sum is 2/3. It converges to 2/3. And what we see is that the r in the geometric series, the constant factor, is less than 1 in absolute value. We require r to be less than 1 in absolute value in order for the geometric series to converge. So this series converges by the geometric series theorem as well as by the alternating series theorem. The series, the sum of a sub n, converges absolutely if the sum of the absolute values of the a sub n converges. This is called absolute convergence. Let's go back to that example of the alternating harmonic series. We see by the alternating series theorem that the alternating series negative 1 to the n plus 1, 1 over n, does converge, but the series of absolute values, which is 1 over n, diverges by the integral test. So this is a series that does not converge absolutely. If a series converges but does not converge absolutely, then it is said to converge conditionally. The alternating harmonic series then converges conditionally. A very important result is that if a series converges absolutely, if the series of absolute values converges, then so does the series a sub n without the absolute value signs. Now let's take a look at some other examples. The sum from n equal 1 to infinity of negative 1 to the n plus 1 times 1 over n cubed. That series converges by the alternating series theorem, but so does the series of absolute values. The sum of 1 over n cubed converges by the integral test. So our first series converges absolutely. Now what happens with the second series? Well, that also converges absolutely, and you could use the ratio test to test for that. You look at the series of all positive terms, 1 over n factorial, added up from 1 to infinity. That is going to converge, and it converges absolutely. So the negative 1 to the n over n factorial also converges. In fact, we're going to learn when we study Taylor series that the sum from n equal 1 to infinity of negative 1 to the n over n factorial is going to equal e to the negative 1 minus 1. So we can actually find the sum of the second series as well. We'll be talking more about series in our next lecture.